Okay, the other numerical method that you need to know is called the Newton-Raphson method. This video is not going to be anywhere near as long as the previous one. So again, we're going to look at a method on how to solve the equation f of x equals 0 for some f of x such that we can't make x the subject. We can't solve it analytically. So we're going to need to employ a numerical method to do so. So what I'm going to do is just going to illustrate exactly how the Newton-Raphson method works. So say we've got our curve, which looks something like that. Let's pop an axis on there, like so. Okay, x-axis, and the curve carries on a little bit over there. Okay, now let's say I'm trying to find this root here, alpha. This is the graph of y equals f of x, and I'm trying to find alpha, which is a point such that f of x equals 0, i.e. it crosses the x-axis. So what the Newton-Raphson method does is it takes a point that's close to the root you're trying to find. Let's call this x0. It's another iterative method like the rearrangement method, so it takes a solution and improves on it. And what we're going to do is we're going to create a tangent line to that point. There's my tangent line. And where that tangent line crosses the x-axis, that is my next approximation. And then I can plug that back in again, and I can find another approximation and so on. And what's going to happen is, as I keep sliding down these tangents, I'm going to get closer and closer and closer to my root alpha. So that's the general idea behind the Newton-Raphson method. Now there is a Newton-Raphson method formula, and I am going to derive it now. It doesn't take too long, but you do not need to know the derivation for the A-level course. You just need to be able to use it. So, just going to draw that kind of diagram out again. There's my axis. There's the alpha I'm trying to find. There's my x-axis. Yeah. And rather than call this x0 now, I'm going to call this xn. And then I'm going to draw the tangent to the curve at xn, something like that maybe. And where that tangent crosses the x-axis, that is the next iteration, value xn plus 1. And the definition of this curve is y equals f of x. Okay, so first of all, we're at xn. We want to find the equation of this tangent line. So we know that this tangent line goes through this point here, which is going to be the point xn, f of xn. Yeah, it's going to be the y-coordinate for that x-coordinate, because it goes through the blue curve. And we also know the gradient of this point, if we can differentiate, is going to be f primed of xn. And that's the point with the Newton-Raphson method. This makes it slightly more difficult than the rearrangement method, is that you've got to differentiate as well. But it does reap higher rewards. It's a much better method. Okay, so the equation of the tangent then is going to be y minus y1, which is f of xn. And that's going to equal m, which is f primed of xn, into x minus xn. Okay, so that's the equation of the tangent. Xn is a known number, f is a known function, f primed, we're assuming it exists, and x and y are our two variables. That's the equation of the tangent. And what we're going to do is we're going to find where this tangent crosses the x-axis. So where it crosses the x-axis is going to be the next iterative value, okay, xn plus 1, and that occurs when y is 0. Okay, so that point is going to lie on this tangent. So that's going to give us minus f of xn, because y is 0, equals f primed of xn into xn plus 1 minus xn. Okay, so that's now xn plus 1 and xn in the same function. So if I just rearrange that, I can make xn plus 1 the subject, and I get xn plus 1, kind of divide by the derivative and then add the xn. Is going to be equal to xn minus f of xn divided by f primed of xn. And that is the Newton-Raphson formula. That's the iterative formula that we're going to be using in this video. Okay, xn plus 1. The next value is equal to the old value minus the function at the old value divided by the derivative of the function at the old value. Okay. Like I said, you don't need to know the derivation, don't need to know all this bit, but I do like to kind of point out where things come from, and that's exactly where this formula comes from. So the rest of the video is now just an example. Not an exam style question, just an open question. Solve sine of x plus x equals 5. Find the root to 4 decimal places using the Newton-Raphson method. So first thing to note is we're not told where to start. We're not told to sketch anything. We're not giving anything. It's very open. It's not an exam style question. So let's just have a look at what this graph looks like. I'm going to graph f of x. And what I need to do is I need to define f of x, because f of x equals 0 is what I'm trying to solve. So f of x therefore would need to be sine of x plus x minus 5. So the equation I'm trying to solve then would be f of x equals 0. Alternatively, it could be the negative of that. It could be 5 minus x minus sine x. I'd get the same root. So let's have a look at the graph of this function. Okay, so we're going to have sine x. Okay, make sure you're in radian mode. Sine x plus x and minus 5. And let's draw it, see what it looks like. Okay, there's nothing showing, so let's change the window. Let's try going from minus 10 to 10. Okay, nope, we've got a bit of a curve there. We can see that the root, there's 9 there. So I think these are all in ones. So it looks like to be between 5 and 6 by the looks of that. You can just check that. If I go back to the V window, if I go from x is 0 to 6, we should get a bit of a clearer view. There we go. Okay, we can see that the root alpha lies somewhere between 5 and 6. And I know the graph, it is actually the only root. And if you zoom out far enough, you can see that. Go further down than that. Let's try minus 100 to 100. And in the y, let's go from minus 10 to 10. Look, there we go. That's the graph. It accelerates down that way and up that way. It's only got one real root. Okay, so we can now use the iterative formula to plug that in. So we know it's a bit bigger than 5, but let's choose x0 to be 5. In an exam question, you would be given where to start, and xn plus 1 equals xn minus f of xn divided by f primed of xn. Okay, that's the formula, which I derived on the previous page. So in this case, xn plus 1 is going to equal xn minus my function, which is sine of x plus x minus 5, and that's going to be divided by the derivative of the function. We're in radians, so the derivative of sine is cosine, the derivative of x is 1, and the derivative of 5 is 0. So back into computation mode. 5 equals, because I'm starting at 5, and then I'm going to put the next answer is going to be the previous answer, subtract the sine of the previous answer plus the previous answer, minus 5, divided by the cosine of the previous answer, plus 1. So x1 therefore is this number. Okay, x1 is 5.74702. The question asks for 4 decimal places. So we'll keep going until it settles at 4. 5.62002. X3 is 5.61756. X4 is 5.61756. That's the same as the previous one. Oh, there we go. It's converged. So we can say that alpha is 5.6176 to 4 decimal places. And we should always check that that is indeed correct to 4 decimal places. And we do that by looking at the bounds. So if I calculate f of 5.61755, it's the lower bound, and f of 5.61765, it's the upper bound, then I'm looking for a change of sign. Okay, it's always good practice to do this, even if the question doesn't explicitly ask for it, although usually it would. Okay, delete that. Okay, so plugging in the function, we've got sine of x plus x minus 5, and we're going to set it from 5.61755 to 5.61765, and we're going to go in steps of 0.0001. Okay, get the table. And again, I'm not looking for necessarily what the numbers are, I'm looking for the signs. So we've got minus 0.000009 for that one, and 0.0002 for that one. So change of sign. Okay, it's gone from negative to positive, so the sign has changed. And f is continuous. Therefore, alpha is indeed 5.617624 decimal places. That kind of confirms that is indeed correct. Okay, that's it. Thank you for watching.